Picture has the inside of the cell right here. There's the inside, and here's the outside. We have these solute particles right here that we want to move across the membrane. So they are in an area of high concentration right here. So if they're in a high concentration, which way are they going to move? Down. They're going to move down to the area of low concentration. That movement from the area of high concentration to low concentration is what we call diffusion. As they move, you get more and more that move across. That's what we see in the second picture. More and more molecules are moving across the membrane. And then finally, when it's balanced on both sides, we have some molecules that go this way, but we have some molecules that move back. When it gets to that point, what is the cell said to be at? So when we have equal concentrations on both sides of the membrane, the cell is said to be in equilibrium because it's balanced. Okay, this dot right here is a solute particle. The next part, this circle area, so this circle area right here represents the actual cell. Okay, so this is the cell. And then the last part, so that's not pointing to the dot, this is just pointing to the white space. So this last one is the actual solution. So this is a water solution. We call it an aqueous solution. Put red, so anything in red, this is going to be the solute. Okay. Okay, everything that I do in, let's see, blue will be water. So blue equals water, H2O. First, we're going to go through here and show the path of the solute. Okay, so I'm going to be using the red one. For the first diagram, okay, the solute particles are spread out evenly. That means they have a same concentration on the outside as they do on the inside. So is there any total movement of the solute in the first diagram? No net movement because it's at equilibrium. So we can draw an arrow moving into the cell and an arrow moving out of the cell to show that solute particles are moving in and moving out because it is at equilibrium. The next one, we see that there is a lot more, don't write this, there's a lot more solute on the outside. And so if the solute moves from an area of high concentration to low concentration, where is the solute going to move? It's going to move into the cell. Okay, because there's more salt on the outside, the salt is going to move into the cell. Similarly, in the last one, there's more salt inside of the cell, so where is that salt going to move? Outside. Okay, so that's the path that the salt takes in each one. The next one we're going to do is the water. Before we do this, though, I want you guys to write a little note right here, that the solute sucks.
Whoa. That's rude.
What I mean by that is imagine that each of these salt pieces has a little tiny straw. They suck or draw the water towards it. So, in the first picture, who has more solute particles? And remember, we're not talking about more, we're talking about a greater concentration. Which one has a larger concentration?
Water.
Yes, the concentrations are equal. So you have some water moves out, and you have some water that does what? Goes in. So because it's at equilibrium, some water comes out of the cell, some water goes in, but overall it's at equilibrium. In the next one, for hypertonic, which one has more salt concentration? Outside. So imagine this has more straws out here. So where's the water going to move? It's going to move out. Okay, and the third one, there are more straws inside the cell, so where's the water going to move? Inside. The last thing, the root words. Iso here, iso means same.
Are those highlighters?
Hold on. Here, hyper means more, and hypo means less. Because of this, isotonic solution has the same concentration inside and outside. A hypertonic solution has more solute in the solution, whereas a hypotonic solution has less solute. So when we see these words, hyper, hypo, and iso, we are talking about the solution on the outside.